Okay, last time we played with GPIO, right? General purpose input output, the most simple IO device, right? Let's talk some more about GPIO. Let's open this one. So I think this is the design we did last time, right? We connected this LED, right? LED is already on the board, right? Okay, good. Okay, those LEDs, 8 LEDs are already on the board, right? And switches and push down button, right? Those simple IO devices are already on board. And what if here? What if you want to connect, these LED, the external LED, which is not on board? What do you have to do? That's what we want to talk about today. And also, what do you have to do if you want to take input from? So that is output, right? From GPIO point of view, you are writing something, right? CPU, right? CPU is writing something. Then LED will be turned on or turned off, right? And this one is a light sensor. And what if you want to take input from this light sensor, which is not on board, right? Board does not have light sensor. You want to connect externally, right? That's what you want to talk about. First, easy one first, this one. So we want to turn on and off this LED. So starting from this one, starting from this design, probably you can add another GPIO like this. Okay, then it is suggesting, okay, I can do some connections. So what you have to do is you have to make two connections. First one is this XC, slave XC, right? So AMBA protocol, if you extend this, there are a lot of signals, right? Input and output signals. So CPU is talking to this GPIO through that connection. So that is AMBA bus. That is one connection. And second is this one. You want to connect that GPIO output to that LED, for example. Okay, that LED. Okay. So what you have to do is, okay, so it is suggesting something. So okay, do whatever you can do. So probably check everything. Slave XC, right? That's slave XC and GPIO. Okay. Then let's see what the tool can do. So it made connection, okay, that device. Okay, and by default, it connected to this button. Button is what? Button is this button. 5 button. That is not what you want, right? This button. Okay, PTN 5 bits, 5 buttons. Okay, 5 buttons. So you remove this connection and double click this to set some configuration. By default, look at this GPIO. So it is connected to this buttons on board. Okay, and if you expand this, and 3 choices, you can connect to LED, switch, and button. But that's not what you want to do. So click on custom, right? Then you have to make your own connection. So expand this. Then you have to be careful, not that output, but one below. Okay. So again, double click this, and IP configuration. That is not. Look at this. That is not input device, right? It is output. Right? You are sending something. You are programming something, writing something. to connect LED, right? To control LED connected to this output. So that is not, input. So all output. How many bits? What do you think? 8-bit? I don't know. So depending on your application needs, right? Probably 8-bit. How about that? Right? Okay. Now expand this. Then now, output. So that got converted to output. This arrow, right? Arrow. So right click on the one below, not this one, one below. Then make external. Okay, make external. Okay, not this one. So not this one. Be careful. But this one. Make external. Okay, by default name is this. Okay, and you can change this name to whatever you want. So probably here. Name is too long, so Gpio 0. How about that? Okay, so anything is okay. Just name. Okay. Then the remaining thing is, okay, we have what? We have Zinc 7000 and JetBot, right? And then we want to connect LED. Connect LED, okay, to our, we have PS, right? PS, and the GPIO we just added, right? And the name, output name is what? GPIO. Okay. So we want to connect that output to, that this node, right? This node. Then what do you have to do? So this one, so JetBoard is offering this expansion slots. Okay. So we want to use those expansion slots. Then if you look at JetBoard user manual, it is talking about that expansion slot. Okay, this expansion header. Okay, this one. Okay, those expansion slot, right? And just one expansion slot, but so probably search with JetBoard schematic, okay, diagram. Then Xilinx is providing schematic of that board. Okay, PCB design board, PCB design file. Okay, so from here you can check out that expansion, right? Expansion slot in detail, right? So here JA1. Can you see the marking? Probably here, marking. I don't know. JA, here, JA1, I think. Is it? Yes, JA1 here. That is JA1 and JA2 and so on, right? JA1, JA1 and JB1. This JA1, this one. And the one on the left, that is JB1. Okay. And JC, JT, JE. Okay. So some detailed connection information. Okay. So from here, so you have also marking here, right? Very small. So can you see the number here? Here, that number. 1 here, 1. It starts from here, right? 1. small marking here. Okay, one means that one. So starting from here, right? That one. Okay. So what you want to do is we want to connect. We want to connect that into JA what? In this example, JA I did JB1. Okay. JB1, and that is already, this is JetBoard, right? That is already connected. That is already connected to some pin, some pin in a Zinc device, right? So you have 8 probably that is connected. Okay, that is connected to Zinc device, right? So what you have to do is we need to figure out which pin that node, okay, that node is connected to. So you need to take a look at that. You need to take a look at this one, right? This schematic diagram and this one, okay? JB1, right? For example, JB1 is a JB1. The first one is connected to W1, 2, for example. Okay, W12, W12. Second one, W11, W11, and so on. Okay. So in the design, going back to our Vivado design. So what you have to specify is that output, that GPIO output is that output should be connected to those pins, right? That is missing information. That should be connected to somehow connected to those pins. Okay, that is missing information for now, right? So how to make the connection? Very simple. You can add a constraint file here, constraint. Okay, so let me copy from my previous design to create. So from the project, okay, the one I did project is open with your close. No. Okay, that constraint. Let me copy this to our design. So here add constraint, add the source. So add all create constraint. No, yes. Add create. Okay, create. So name GPIO. Okay, GPIO. How about GPIO constraint? Finish. Okay. Set the meaning, nothing. So copy and paste. So in the name GPIO 0, right? 8-bit. So we don't need those constraints. Let's remove it. Look at this, right? GPIO 0 that is connected to W12, right? And GPIO 1, W11, and so on, right? And so on. So that is constraint file. Okay. So we have that missing information now, right? That missing information is resolved now. That's it actually. So that's what you have to do in hardware design, right? So we did everything. Okay, then to synthesize and place an out. Before you do that, you have to generate top HDL file. That is standard procedure in Xilinx. Okay, check out generated HDL. So we have Gpio underscore 0 that got generated. Okay, and that is output. Okay, this name, and double check this constraint. We are using right name, Gpio 0. I think it's correct. Okay, then generate bit stream. Okay, so while it is doing synthesis and place and route, let me explain about that breadboard. Okay, probably some of you never used that breadboard before, right? So let me explain briefly. Sensors, I think this one. This is slide, right? Sensors, lecture 1.5. Lab supplement, okay. Okay, this breadboard. So I teach. I taught some some course dealing with Arduino. Arduino board, right? So if you have experience in Arduino, then probably this board is not new to you. So anyway, this is called breadboard, and the thing you have to be careful is this. The thing you have to understand. The dot, these dots in horizontal line. How many dots? 5, 5, 5, 5, 25, right? 25 dots are connected together. Okay, and this upper also upper 25 dots. Those dots are also connected together. Okay, and this vertical, these 5 dots each, 5, 5, 5 each. Okay, these dots are connected together, and this one too. So these 5 connected together. Okay, so typically this plus plus is providing supply voltage to the circuitry you are creating here, and minus is supplying 0 volt or ground to the circuit. So here, if you look at this, the connection, look at this. So look at this. The black, okay, black is what? So we typically use black line to connect 0 volt. If you Google search with power supply in computer. So we key page power supply. Then so people use some convention. So what convention? Color coding, right? There. Okay, here. Okay. Black. So here, right? The power supply, right, in computer, right? So you have black, a red, a yellow, and so on, right? Those lines, right? So typically black means ground. Ground is what? 0 volt. And red means 5 volt. Okay. Yellow typically means plus 12 volt and so on. Okay. So we use that convention. Better to stick to that convention when you creating your custom circuit. Okay. So you look at this. That black is ground. Right? Black is ground. How do you know? So that is ground. This expansion slot output. Okay. Second from second second from the left, right? Okay, it is done. Okay. Engine slot. Okay. Board schematic. Look at this. Okay. JB1. So we are talking about JA1. This is slot. Okay, JA1. And this one is JB1, right? JB1. And number 1, right? You start from number 1, right? 1. So second from the left. Second node from the left, that is GND ground. Right? And the leftmost node is applying voltage 3.3 volt. So we connected that ground to this LED, and the other output, the other node is connected to number 1. Right? So here number 1, that one, GPIO, right? GPIO output. Okay. Okay, that's one thing you have to be careful. You have to know about this breadboard, and also you have to know about this LED itself. That LED. This LED is providing 2 legs, right? This long leg and short leg. This long leg should be connected to positive side voltage. And short one should be connected to negative or ground. Okay, so look at this. Right? If I look at this, right? We have long. This one is long and short, right? I connected long to positive side and short one to the ground. Okay, so you have to be careful about that connection. Okay, that is a connection I made, and then okay, so close one Vivado. So that is implemented design. Then check out this, GPIO, right? IO port, GPIO output, our GPIO, right? IO device that is connected to, look at this, W12 zinc pin, GPIO 1, W11, and so on, as we defined in the constraint file, right? So implementation is done, hardware is generated. What you have to do is export hardware. Okay, test class. Okay, test class. Okay, then software development. Okay. Not this one. Test class. Okay. This is the one we played with last time. But the thing is, hardware got changed. Probably you have to regenerate this, hardware platform because hardware got changed, right? So let me do this. New platform project. Okay. So GPIO custom GPIO hardware platform. Okay. take the folder. It doesn't. Desktop. Test is the one. Test classes. Okay, this is the one. Okay, finish. Okay, so platform project got generated. So compile it. So essentially, this a custom project is providing some low-level APIs you can use in your application program, right? But in our class, we don't want to use, the APIs this platform project is providing. You want to do everything. We want to do everything from scratch, right? So here, file, application. Okay. So platform, which platform do you want to use as a basis, custom GPIO we just created. Then application, custom GPIO application, right? Simple app. Okay, hello world. Okay, hello world. Okay. Okay, then probably now we can play. We can write C code, right? We can write C code here after initialization. I don't know what it is doing, but let it execute what it has to do, right? Then we can probably turn on that LED, turn on, turn off that LED, right? For that purpose, we need to know the base location. So from our block design, okay, close too many things. Address editor. So new GPIO device. Is it GPIO 1? Okay, confused. GPIO 1, GPIO 0, right? GPIO 0 and 1. So 1, it starts from 4121. That is base location in memory map. Okay, 4121. So we define what? Pointer variable, custom GPIO, okay? Pointer, right? 4121 location, okay? So it is pointing the location, byte location. We created, we have 8-bit connection. So probably cha would be okay, not unsigned, right? Unsigned cha, how about that? Not unsigned integer, cha. Okay, then unsigned, cha. It is pointer, right? This location is pointer. Okay. Then probably before initialization, we don't want to, execute this, right? So here, write custom GPIO and turn on 0x01. How about that? Turn on that bit. Okay, supply some voltage to this LED. Okay, and turn off. How about that? And also while. Okay, how about the while? How about this code? Okay. 1 to write 1 to the register location, 0 to the location. Okay, compile it. on the board. Okay, then debug, launch. Okay, create new session. Okay, then debug. Okay, then register. Okay. F5. Okay, so moment of truth. If I press F5 one more time, probably this LED will be turned on. How about this? Turned on, right? And turned off. Turned on, turn off, turn on. Okay. Okay. Any question about this? And one thing you have to be careful is actually, when you connect the LED, typically this LED manufacturer suggests, okay, better to connect this register. Okay, do not directly connect this LED to power supply because too much current would be flowing if you don't have a register. That means you can burn, that would burn this LED. But I did some experimentation. If I connect a register is typically 200 ohm to 300 ohm, that range. Okay, so I distributed the packet, right? So whole packet to you, so you can find register within that range. So the first time probably you can connect. So you can connect like this. You can connect register. Okay, so register between these two nodes. So like this, then put register between these two. Okay, then if the LED is too dim, then probably you can remove and connect directly like this. If LED is too shiny, then better to use that the register. Otherwise, that LED will be destroyed. Okay. 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 So in this way, you can connect the LED and control this LED turning on and off. Okay. So okay, let's move on now. So we want to go further. Okay, now we want to take input from this light sensor. Okay, so that is analog. It is important, right? Analog input, not digital input, right? So light sensor means what? If you block this sensor, then okay, let me show you this board. So light sensor, slide. This one, light sensor. Okay. If the ambient light is too bright, then resistance goes down. And if the if that is in dark place, then resistance goes up. Okay, resistance of this light sensor goes up. So we use that property to take input from light sensor. Probably you better I need to explain that Ohm's law first. Okay. So Ohm's law first. Ohm's law is defining the relation between voltage and current, and resistor. Very simple law. So if you go to electric engineering department and electronic engineering department, that is the first one you learn. That is electric circuit 101, actually. Very basic thing. So you have power source, okay, power source. For example, battery, right? 1.5 volt battery. So 0 volt here, and 1.5. And how much current is flowing between these two nodes and resistor? Okay, so current and resistor. So V, voltage is equal to I and R. Okay, that is the law you have to remember. Very simple law. Okay, so you can think of voltage as a height. Okay, so water is flowing from higher place to lower place, right? So that is a voltage. And the water, you can think of it as current. Water, current. How much current is flowing between these two? Depending on the resistor, the surface resistor. Resistor is too high, very high. R is very high. Then small current is flowing because resistor, right? You are resisting, right? This guy is resist. Okay, you cannot flow between these, these 2 points. Okay, if resistor is small, R is small, meaning the surface is very smooth, then a lot of current, a lot of water is flowing, right? That is analogy. Okay, so V is equal to IR. So remember that. So we are going to use. You need to know that simple law. So the one example is, what if you have 5 volt here? 5 volt. Okay. This one is ground. Okay. So that is ground. Ground means 0 volt. Okay. And here you have 2 ohm and 3 ohm. Okay. And what is the voltage at this node? V. So if you compute the current flowing between these 2 points, 5 ohm, right? So V is 5 volt, and this is R. Current is equal to R, right? So that means 5 volt, 5 ohm. So 1 amp is flowing these two, right? 1 amp. So 1 amp means the voltage between these 2 points, then what? V is equal to I and R. So 3 volt. Okay. And voltage between these two. Same current is flowing. Same wire, right? Same wire. Same current is flowing these two. So V is equal to IR. So 2 volt. Right? So 5 volt, 5 volt, right? So the node, so the voltage at this node will be 2 volt. So voltage is distributed between these two. Okay. So 5 volt, 3 volt, 2 volt. So same current is flowing, right? 3 divided by 3. 3 volt, right? Divided by 3. So 1 amp, right? And 2 divided by 2. So 1 amp. Same current is flowing. So the voltage of this node will be 2 volt. That's that's what you need to know. Okay, hold on. Okay, that is what you have to understand and know to connect this to connect this light sensor. Okay, so think about this. Okay, think about this. Now think about the circuitry on the right side. On the right side. Okay, so photoresistor means light sensor. That sensor. Okay, and you have some resistor. Okay, you have some resistor which is 10k ohm. Okay, and you have light sensor. Okay, light sensor, and this one is what, 5 volt. So we want to figure out the voltage. Okay, so we are going to take that, we are going to tap this line and use it as input to zinc device. Okay, so light sensor. Think about that. The ambient light is too bright. That means what? Too bright. Light intensity goes up, then resistance goes down, right? R is very small. R goes down. And what would be the voltage of this node? Roughly. Okay. For simplicity, let's say light is very shiny, too bright, then R goes down. And let's say for simplicity, okay, too bright, then R is 0. Because R is 0, R goes down, right? To the extreme. We will talk about the extreme case, right? R is 0 because too bright. Then the voltage of this node would be equal to this 5 volt, right? Zero resistance, right? 0 ohm. That means that is directly connected to that guy, right? So 5 volt, right? Input is 5 volt if too bright. Five volt if shiny, okay? Shiny, too bright. What if the ambient light is too dark, very dark? Then R goes up. Right? And what is the voltage? What will be the voltage of this node? R goes up. Okay. So for simplicity, let's say R will be infinity. Infinity, right? R goes up for simplicity, right? Then what would be the voltage of this node? Infinity means what? Infinity means it is actually disconnected, right? This node is not connected. This is disconnected. Air, like air, right? Air, right? The resistance is infinity, right? So that means the input voltage would be equal to this 0. That is how you analyze this circuit. Okay, that is there is a way, probably. There is an easy way to analyze the circuit. The point is, if the ambient light is very bright, then this node is close, right? Not 5 volt, close to this one. Okay, if light is too dark, too dim, then this voltage is close to 0, Okay, And check out this circuitry I created here. Okay, so if you look at this circuit, okay, this circuit, simple circuit. So what I did is very simple. Let me draw a circuit diagram. Okay. So by convention, this red one, red is 3.3, 3.3, and this black is 0, right? So I connected like this. Here are two resistors. Okay, this one is 3.3 volt. Okay, so I drew that side, red one and two resistors. Okay, then you have light sensor, and that is connected to ground, 0 volt, black. Okay, this one, this black. So expansion slot, right? The leftmost one is providing 3.3 volt, and second from the left that is providing 0 volt. Okay, so I tap. Look at this. I tap that line. So yellow is applied to connected to somewhere, right? So expansion slot, right? So I tap that line, tap this line, and connected to some node, some slot, some slot on JetBoard. Okay, and not only this, I also connected. Look at this gray. Look at this gray. Connected this one to 0 volt, right? To JetBoard. That is the circuitry I created. Okay. Then this register, I think. Okay, I lab supplementary. Okay. So I have to go back and forth. Okay, this one, this one. So check out this. Okay, this one. I created that circuitry. Okay, so look at this. So each one is 10 kilo ohm. 10 kilo ohm, 10 kilo ohm. Okay, so 3.3 volt and 10 to 20 kilo ohm. Okay, so somehow I want to control by placing your finger. By placing your finger on this light sensor, you can control the voltage of this node. Okay, so so roughly, if intensity light is too shiny, then what happens? If shiny, okay, if bright, okay, if bright, then voltage, this voltage, input voltage would be what? Shiny, then resistor goes down, right? Resistance goes down. So for simplicity, you can think of it as a zero ohm. It's directly connected. So it is going to be close to 0 volt if bright. Right? If bright, resistance of this sensor, okay, goes down. Okay, for simplicity, let's say it is 0 ohm, then directly connected, right? That is directly connected. So input voltage is going to be close to 0. If dark, okay, then resistance goes up. Okay, for simplicity, okay, let's say it is infinity ohm. Not infinity, but infinity, right? Okay, so then the resistance, the voltage, input voltage is going to be close to 3.3. Okay, 3.3, close to 3.3 if resistor is infinity. but in reality, the resistor is not infinity. Okay. In reality, that going to be close to actually 1 volt. Actually, one volt, because current is flowing. Current is flowing, and this voltage, supply voltage, will be distributed. Okay, here and here and here. Okay. So by using that difference, you can check. Using software, you can check. By reading this voltage input, you can figure out if the ambient environment is bright or dark. But the question is, it is not digital information. You are taking analog input, right? Depending on the location of your finger, right? Your location. Depending on the location of your finger, right? If the finger is completely blocking the light, then what happens? Completely blocking the light, then resistor goes up close to 1 volt. But if the finger position is some you have some gap between these two, then you see you get different voltage level, right? So it is analog information. Okay? So to get that information, the analog information, but to process it in digital format, you have to have some other component called ADC, analog to digital converter. So it is taking analog input and providing digital information. Okay. So that is a background. Okay, that is a background, and let me show you how to use XDC, analog to digital converter in Xilinx. Actually, it is very simple. Okay. I did all the dirty work, so you just follow. Okay. So what you have to do is very simple: instantiate ADC. Okay, XADC. Then also it is offering connections. Okay, run connection automation. You have XC Lite interface. Through that interface, you can set configuration, and also you can read some information about that digital information. Okay, so run connection automation. Okay, XC Lite, then okay. Okay, then a tool made that connection. XADC got connected to this PS through that slave connection. Okay, so probably you are curious. So why so many output signals, right? Double click this if you want to know. Okay, so ADC setup. So you can check out the manual. I don't want to go through everything. Actually, I don't know everything about this XADC. I know very simple thing. Okay, so if you want to know detail, then check out the documentation. This documentation, the one I posted on class page. Okay, using that XC Lite, I want to set configuration and read some information. XDC setup and single channel. Okay, so we want to take input from this BPBN. Okay. Okay, so that is this one is going to be BP. This one BP and this one BN. BPBN. We are going to take input. Then ADC setup. Probably you don't have to worry too much about this alarm, right? So if you uncheck this, it has also temperature sensor inside and some voltage sensor. Some voltage sensor. You can, if you uncheck this, look at this. Uncheck this. Some alarm output. Okay, like voltage level is too high, then it is triggering some alarm. So you can do this. Okay? Turn off if you want. Okay. So temperature sensor enabled and so on. So, okay. So and one important thing is you have to make that connection. Okay. VPVN, because we are going to use that connection to take input. So make it external. Okay. VPVN 0. So in this case, you don't have to add some constraint to this file, because in JetBoard, if you look at the JetBoard, expansion header, right? Expansion header. So this one, we have a dedicated slot that we have. This dedicated slot for taking analog input. So this one, this VP, VN, some other analog external input, if you have, right? If you can connect your own, the analog signal to this input. So that is already determined, right? So Vivado already know about that slot. Okay, so you don't have to have separate constraint to connect VP, VN. Okay, so let me compile it. Let me synthesize it. Before you synthesize, you have to generate HDL. Okay, so scroll it down. We have this input, right? Two inputs, VPBN, two inputs. Okay, now, so generate bit stream. Okay, while it is generating bit stream, let's go to slide. Okay. So let's read some of the thing. Okay, let's go through from the start. Okay, XADC. So we are taking XADC is taking analog input and generating some digital information. So how does it work? So it is taking, so internally it's taking some samples, actually a lot of samples, and quantize the data is sampled and generate the code, generate the 4-bit information. Okay. So here we have a PS, and ADC is also hard macro. It is fused into the PL section. Okay. To use it, you can just instantiate and connect, make the connection. Okay. So that is the design, example design. And let's read some of that. This one, Guyun, can you please read this one?
X86 in Zinc 7000, 12-bit 1 megasamples per second, up to 17 external analog input channels, on-chip thermal and on-chip voltage sensors. The X86 has two 12-bit 1 megasamples per second ADCs with separate track and hold amplifiers. An analog multiplexer up to 17 external analog input channels and on-chip thermal and on-chip voltage sensors.
Okay, thanks. That is enough. So it is generating 12-bit output. So here, going back to here. So here, it is taking input, analog input, and generating 12-bit output, okay, XADC. So 12-bit output. So how many samples it is taking? 1 million samples every second. Okay, so these samples. It is taking 1 million samples every second. Okay, then this one, it can take up to 17 external analog input. So next one, okay, like this. That is a block diagram of XADC. You have two analog to digital converters. And using this multiplexer, analog multiplexer, you can select which one do you want to send to ADC. Okay, VPBN, or this one, and so on. Okay, and it has a temperature sensor and some voltage sensor. So you can you can take sample also of this voltage and temperature sensors. Okay, then this one. Himin, can you please read this one?
Unipolar mode. Figure 2-2 shows the 12-bit unipolar transfer function for the ADCs. The nominal analog input range to the ADCs is 0 volt to 1 volt in this mode. The ADC produces a zero code when 0 volt is present on the ADC input and a full-scale code of all ones when 1 volt is present on the input.
Okay, let's just stop there. Okay, right, can you continue until this point?
The ADC output coding in unipolar mode is straight binary. The design code transitions occur at successive integer least significant bit values such as 1 least significant bit, 2 LSBs, and 3 LSBs, etc. The LSB size in volts is equal to 1 volt divided by 2 to the 12, or 1 volt divided to 4096 equals to 244 microvolt.
Okay, thanks. So according to this specification, in this operating mode, unipolar mode, ADC, okay, this ADC converter can take that input, what input? 0 to 1 volt input. That is important. That is why I did, all the dirty work to create that circuitry. So the input, okay, this circuitry, I changed it, this register. I changed these register values to make sure ADC take this voltage can be up to 1 volt. Okay, 1 volt, because the specification, ADC specification says you have to make sure you are supplying up to 1 volt or less, up to 1 volt, right? So 1 volt or less. That is why I created a circuitry, right? So if bright, close to 0, dark, then register goes up because voltage is distributed, then it is supplying close to 1 volt. I did all the dirty work, right? So look at this. So this, so this one, look at this. So I measure the voltage, okay, like this. Okay, so I block the light and measure the voltage using this multimeter. Okay, so look at this. The voltage between, so supply voltage first, right? Supply voltage from here to red one to ground, 3.3 volt. supply voltage. This is supply voltage, right? Supply voltage, 3.3 volt. And then I try to measure this voltage. When I block the light, then what would be the voltage? When I, unblock, then what would be voltage? Look at this. When I block, then the voltage is 0.87 volt. It is not exceeding 1 volt. Okay, and if you unblock, okay, so this open state, then voltage 0.17 volt. So I did some manipulation. Okay, I added this register to make sure I'm supplying up to 1 volt. Okay, and then one last thing. So one thing probably you want to understand is this. So this look at this graph. Input voltage to ADC, and output coding, output digital information. Okay, so it says, a spec says you can provide up to 1 volt, 1 volt, up to 1 volt, right? And this 1 volt, okay, so 1 volt, let's say, I don't know, it's 1 volt. This 1 volt signal, something like this, it is sampled. Sampled here, sampled here, sampled, right? Sampled here. So that analog information should be converted to a digital information using 12-bit digital information, right? So 1 volt, for sure, that is going to be 0x FFF, okay? 0 volt, that is going to be, 0, right? 0 volt, right? So this one. So in between these two, you can do the simple, simple math. 1 volt divided by 4096, which is 2 to the power of 12. Right? You can then check out the resolution, sensitivity. Right? If you do this math, then you get that number, 244 microvolt. Okay. So input voltage is between 0 to that number, 2.44 millivolt, I think, millivolt, right? Then ADC will provide 0. Next step, right? Okay, this number and 488. Then ADC will provide 001, and so on. Okay, so 1 volt, 1 FFF. So that is sensitivity, right? Or resolution, right? I think that is done. Then this is the register you have to read. I don't want to go detail. To use that ADC, you have to set configuration. Okay, before you use ADC configuration, then after that, you can just read that register. Which register? Data register or status register here. It sounds very strange, but status register. And according to the specification, look at this. This one, Kiwon, can you please read this one? Note.
The ADCs always produce a 16-bit conversion result. The 12-bit data correspond to the 12 MSBs in the 16-bit status registers. The unreferenced LSBs can be used to minimize quantization effects or improve resolution through averaging or filtering.
Okay, so the important thing is this ADC output, right? 12-bit output that is stored in upper 12-bit, in 16-bit register. Okay, so that is so what does it say? MSB justified. It does, okay. Anyway, upper 20-bit. that's what you have to remember. Okay, so implementation is done. Okay, then no, open. Okay, reload. Okay, then IO port. Check out this IO port. This BPBN. BPBN is mapped to. This BPBN is mapped to M12 pin, and this one, okay, that is mapped to L11. Okay, in zinc pin. Okay, so you don't have to have separate line for in constraint file. Okay, because tool. This Vivado already know about that information. So now export hardware. Okay, next. Okay. Okay, overwrite. Yes, overwrite. Then software tool like this. This one. Okay, so now create a new platform project. X ADC hardware. Okay. Platform project. Browse. This one, right? Test class. Okay. Finish. Okay. Compile it. Okay, now application project. Okay. That is the basis. Okay. ADC hardware. Next. ADC app. About that. Okay, next. Hello world. It's okay, probably. Okay, then hello world is not the application, right? You want to execute. So let me open. Let me copy the one I created. Desktop, I think. Desktop. Which one is the one? 21. X ADC software. App, I think Gpio. Source. This one, I think. Yes, this is the one. Okay. So XADC registers. Then at the end, it is keep checking, keep checking that sensor, the input. So let me simply copy this. New file, assembly code, adc.s. Okay, copy everything. paste. Okay, main hello. Rename this to main hello. Okay. Yes. Compile it. Okay, so compilation is done. So what I'm doing is I set configuration. So I'm going to leave it to you the meaning of this value. Okay, but that is in the PowerPoint. Here. So this configuration. So configuration register 0, 1, 2. So I program those registers with the value. I'm going to leave it to you. So meaning of that, the value. Okay. This, this one, 9, 1. Look at that. Right. So 9103, and then 300, this one, 400, this one, and so on. And then at the end, the status register. So you need to read that status register. Okay, that is the one. ADC, VP, VN address. Okay, so keep reading, storing it to R3 and R4. So a little bit, it is not, organized. Okay, I did. Okay, so debug, create new session, debug. Okay, so it is turning on that LED. Okay, the one that LED. Okay, that LED. Okay, just for test. Oh no. Okay, address is different. Okay, so address is different, so that is why, right? 4121 is supposed to be 4121. It doesn't matter. Oh, then base location. We have to be careful about base location. So base location 43C0. 43C0. You have to make sure that otherwise 41C0. 43C0. Is it correct? 43C0. 43C. Oh, that is correct. Okay. So let me do this. Register. Okay. Then now keep looking, right? R3, R4. Look at this. R3, R4. This value. R3, R4. 3, 6. Okay. So let me block. While it is running, let me block this. Changed, right? Value got changed. If I unblock, open, got changed, right? Small value. Block again. And depending on the distance, the value got changed. See, completely block. Then look at this. I touched it. D5, write something. Now open. Okay, you can test. You can test it yourself. Right? Any question about this? So this one is going to be very closely related to the class project. So you better do experimentation with the light sensor and XADC. Okay. So I'm going to ask to run some real-time operating system and run some multiple tasks. One task, take input from light sensor, and the other task is, for example, turning on LED or rotating some actuator, motor, something like that. So that will be part of your class project. Okay, that's it for today. If you don't have any question, I'll see you next time. Okay, bye. Okay, thanks.